Hello, George.
Hello, good afternoon.
Good afternoon. Okay, we will just start. Still, there is 10 minutes, I think. Yeah, 10 minutes. So we will wait. Sanjay Kumar Dev, very good. Welcome, Sanjay. Dr. Aryanath. Please introduce Dr. Aryanath. So many people will join today. Hello, Arya. Your voice is breaking. Okay, Arya. Yeah, where are you? Which organization? Oh no, your voice is not there. Okay. Good, Sanjay. Welcome, Istavan. Shankar. Istavan, how are you? After a long time.
István, put your mic audible.
Istavan.
Good afternoon, everyone.
Good afternoon. Oh, good. Color has also joined. Yeah, Vishayji.
There we go.
Yeah, so another 2 minutes and we will start. Hello, welcome everybody in IBAAS lecture series. And today there will be a presentation by a leading alumina technologist, György Bánvölgyi, on the topic Bauxite online analyzers and AY ratio control in alumina refinery. So we will run the recorded presentation of György, and then the session will be open for discussion. So we'll request IBAAS office to run the presentation where György will introduce also. So György, if you want to tell something, or shall we start directly the presentation?
Well, just a second. I think it is the time to start the presentation,
Yeah.
and I hope that afterwards there will be comments and questions.
Yeah.
Thank you.
Yeah. Afterwards there will be questions. It is just 40 minutes presentation, I think, and so there will be enough time for questions and answers. So Priyanka, please put on the presentation, and we are going on silent mode.
Ladies and gentlemen, the title of my presentation, which was prepared along with Dr. Ashok Nandi, senior process geologist, is Bauxite Online Analyzer and A to C ratio control in Alumina Refinery. As I understand, Ashok has introduced me, so I'd like to mention only that when I was graduated, I was specialized in process automation. Let me skip the personal data. The bauxite, as you know, is highly heterogeneous in nature, and despite efforts for thorough blending, it is not always feasible to get uniform grade of ore. The process bauxite moving on conveyor belt is hourly sampled, and the analysis of day composite is normally available after 2 days. Consequently, a critical decision, that is the test tank liquor and solids ratio, is based on the average ore quality, which leads to suboptimal digestion efficiency. Installation of an online analyzer on the conveyor belt provides real-time alumina and silica measurements, enabling precise adjustments for optimal solid-to-liquor ratios and digestion efficiency. The under and overcharge of bauxite in the desiccation digestion process step can be avoided if available alumina and reactive silica of bauxite is known. Here is a graph taken from Peter McIntosh. This line is the caustic profile, which is obviously a disturbance of the ratio control. And here are the points of the analysis and the steps if the bauxite charge is based on the analysis. There is a certain period of time when the bauxite is undercharged and other period of time when the bauxite is overcharged. If the bauxite is undercharged, part of the digestion capacity of the test tank liquor is not utilized. More bauxite could be charged into the test tank liquor, the production rate of the digestion and therefore the refinery could be higher. Part of the test tank liquor is heated to the digestion temperature unnecessarily. In case of the bauxite is overcharged, means part of the soluble alumina does not dissolve and is lost with the bauxite residue. This part of gibbsite comprises seed for premature formation of precipitated gibbsite during the decantation of bauxite residue and also lost with the bauxite residue. And this may cause scalings on the control filtration cloth. Let me go through a few options for the bauxite analyzers. There is one here, the near infrared technology of spectraflow. It provides elemental and mineral phases analysis, large measurement area, and 150 scans per minute. It provides only
Whoop.
Device cross-bell analyzer by Analytical. It utilizes the second option is of belt load variations. No requirement for variable belt speed drives to compensate for belt load variations. Actual 1-minute analysis values. The second option is the control neutron activation device crossbell analyzer by Analytical. It utilizes advanced pulsed fast and thermal neutron activation technology, no radiation hazard, and uses electrically controlled neutron source. It is associated with high penetration capacity and leads to excellent output. Measures uh, hydrogen, carbon, oxygen, alumina, silica, iron elements, and moisture content as well. The third one is the laser-induced breakdown spectroscopy of Lindsay's company. Its source of energy is a solid-state pulsed neodymium-doped yttrium aluminum garnet laser. Provides simultaneous quantitative elemental analysis of bulk material. Completely safe, no radioactive emission. Uh, it is associated with low maintenance expenses, uh, only 20,000 US dollar over 10 years, uh, opposite to the prompt gamma neutron activation analysis. And its measuring rate is 1 to 20 times per second. Uh, why to choose controlled neutron activation crossband analyzer? It uses neutron having high penetration capacity, direct elements measuring potential without mineralogical data, effective in analyzing non-homogeneous material due to the high penetration capacity, accuracy in measuring material with high moisture content, easy installation and maintenance. Meanwhile, the two other options both are surface techniques penetrating only few microns, missing internal composition. Focuses on mineral phases, not on elemental composition, which leads to low accuracy. Due to surface technique cannot handle non-homogeneous material. The NIR requires regular cleaning of halogen light source. The LIBAAS needs periodic cleaning of the laser-induced technology as well. Here is a flow diagram how this device works. Here are three mining areas, a stockpile of the crushed bauxite, a stacker reclaimer which puts the bauxite onto the belt conveyor, and here is the CNA crossbelt analyzer located. Let me go to the other type of industrial analyzers. This is the target is the analysis of the composition of the industrial Bayer liquors. As you know very well, the Bayer liquor solution consists of ions such as sodium hydroxide, aluminate, silicate, carbonate, chloride, sulfate, oxalate, and other organic materials. The conductivity meters measure the total concentration of ions, therefore it is not specific for any particular ions. However, the concentration of most of the ions in the liquid phase of the digestion effluent uh, does not alter rapidly, whilst formation of aluminate anions at the expense of hydroxide ions by the dissolution of gibbsite causes rapid changes in the hydroxide ion concentration and can be monitored by a conductivity sensor if it is properly selected and applied. Here is the well-known equation of the formation of aluminate anion from gibbsite and hydroxide ions. Uh, Basically, there are two types of conductivity measurements. One is the conducting conductivity. Uh, these measurements are restricted to applications where the conductivity is fairly low, the sample is not corrosive and free of suspended solids. This is obviously not the case for the Bayer liquors. The other is the inductive conductivity, which is sometimes called toroidal or electrodeless conductivity. An inductive sensor consists of two wire-wound metal toroids encased in a corrosion-resistant plastic body. One toroid is the drive coil, the other is the receiver coil. The sensor is immersed in the conductive liquid. The analyzer applies an alternating voltage to the drive coil, which induces a voltage in the liquid surrounding the coil. The voltage causes an ionic current proportional to the conductance of the liquid. The ionic current induces an electronic current in the receiving coil, which is measured by the analyzer. The induced current is directly proportional to the conductance of the solution. The toroids do not need to touch the sample. They can be encased in plastic, allowing the sensors to be used in solutions that would corrode metal electrode sensors. Inductive sensors tolerate high level of suspended soils, and these sensors are ideal for solutions of high conductivity, therefore for Bayer liquors as well. Here is a schematic what I have just briefly mentioned. These are the both coils are encased in a single sensor body and overmolded with plastic. The coils must be completely submerged in the process liquid. Here there are two types of conductivity sensors in the market. This is the embodiment of the Rosemont toroidal conductivity sensors. The other is practically the same by Foxborough, and in the leaflet it is highlighted that it's been used in various alumina refineries for the alumina to caustic ratio control. The other type of these toroidal conductivity sensors is the flow-through toroidal conductivity sensors. This is also being used for alumina to caustic ratio control. It is it has a diameter up to 100 millimeters. These sensors can be applied at 145-50 degrees centigrade without any difficulties. In fact, up to about 200 degree centigrade. And the corresponding pressure is tolerated as well. I have made small calculations for the free caustic concentration as equivalent sodium hydroxide for an alumina refinery. It was arrived at 3.3% as equivalent sodium hydroxide. Here are conductivities of some common solutions. This graph shows the sodium hydroxide, and you can see that at 3% of sodium hydroxide, the conductivity is about 200 microsiemens per centimeter. Let me skip to the residence time distributions for continuously stirred tank reactors and a tube reactor. Here is the case when only one tank is applied and the pulse of a tracer continuously leaves the tank, and when there are various numbers of the tanks in serially connected, the shape of this time distribution curve is definitely quite different. And here the blue line shows the shape of the curve of a pulse tracer for a plug flow reactor or for a tube type reactor. This is the residence time distribution plot for two options. This is for reactor cascade of four tanks, and this is the plug flow, and the other type of the same of the cumulative residence time distribution of plots. This is important when we use these various type of reactors. There are various and benefits and drawbacks of feed-forward and feedback A to C ratio controls. As you might be aware of that, the fundamental process control strategies are the feed-forward and the feedback control. The feed-forward control is associated with difficulties with the measurement of the precise mineralogical composition of the solids and concentrations of the liquid phases, also with the solid content of the dense slurry. In case of a feedback control, ideally the A to C ratio of the liquid phase exiting the digestion reactor should be measured and controlled. There are refineries, while the alumina to caustic ratio of the digester effluent is measured by a conductivity sensor. However, in most of the refineries, the A to C ratio of the blow-off slurry is measured since its lower temperature and pressure that is close to the atmospheric boiling point, and this is more convenient to operate. On the other hand, the blow-off slurry is subject to more disturbances. The optimal locations of a conductivity sensor is indicated in the following flow sheet. However, the feed-forward and the feedback controls can be combined. Generally, this combination provides the most accurate control. Uh, Here is the well, conceptual flow sheet for a low temperature alumina refinery. The red line shows the bauxite slurry and the bauxite residue. The yellow shows the digestion liquor, pregnant liquor, and the spent liquor. However, here the X shows where these A to C ratios can be placed. One option is the effluent slurry of the digestion reactor. The other, as mentioned, is the blow-off tank. An interesting question: where should the setup point, with other words, the target A to C ratio, be? In the conventional process control design, several alumina refineries have used a safety margin of 0.05 A to C ratio, with other words, 50 points of safety margin. The safety margin is defined as the difference between the target A to C ratio, the setup point, and the equilibrium A to C ratio. Several alumina refineries use the formula of the landmark paper of Rosenberg and Haley for the calculation of the equilibrium solubility of gibbsite. It is deemed that the A to C ratio points uh, follow the normal distribution around the average. Looking at the curve of the normal distribution, where the standard deviation is indicated, it can be seen that 99%, 99.7% of the points is within a range of plus minus 3 sigma, where sigma is the symbol of the standard deviation. Meanwhile, uh, uh, the plus minus 4 sigma means that 99%, 98% percent is the range when the points can be found. So it is believed that if the safety margin might be about 0.015 from the equilibrium, it can be attained in case of a precise A to C ratio control. This is the well-known A to C ratio graph of Jan Kotte, and here is a to C ratio points of a alumina refinery in Latin America. Just to remember how it looks like. That's the range what I have mentioned. I could found only plus minus 3 sigma, but as mentioned, the plus minus 4 sigma would provide a much wider range. Let me show you the experimental data of kinetic studies of digestion of a gibbsitic bauxite at 150 degrees centigrade. It showed that the actually achieved A to C ratios is higher by about 8 to 10% that is suggested by the Rosenberg and Halley formula. These points are the calculated A to C ratios. This is it suggests that the actual A to C ratios could be higher by 8-10% than the Rosenberg and Halley formula suggests. This is the A to C ratios of actually the same kinetic tests, but up to 60 minutes, and you can see that after 6-10 minutes the A to C ratio practically does not change. Here is the summary of the A to C control and the tentative analysis of the benefits. As per the author's view, the most advanced A to C ratio control is based on a conductivity sensor that is placed for the effluent, for the digestion effluent of the digester reactor. Let it be a tank reactor cascade or a tube reactor. The conductivity meter should preferably be calibrated to the A to C ratio. Two conductivity meters are preferred to be used for a single digestion train. This is a little bit similar how the most important measurements are doubled in an aeroplane. The flow rate of the predesiccated slurry should be adjusted by the controller so that the A to C ratio be kept constant. A tentative calculation has been arrived at about $3 to 5 per ton of alumina product for the benefits of an up-to-date A to C ratio control. A moderate estimation of 1% increase in the digestion extraction efficiency and an estimated saving of 5% in the process steam consumption due to the higher setup A to C ratio have been calculated with. For a given refinery, a targeted process audit should be carried out for a more reliable estimate. In case of an 1.5 million per ton of alumina refinery, the annual savings therefore is estimated to be $4.5 to 7.5 million. The costs and benefits more precisely should be elaborated as next stage. Thank you very much for your attention. The authors are looking forward to your questions and or comments.
Yeah, it's open for discussions and questions. Please welcome to ask questions.
György,
Is it Shankar?
Yes.
Yeah, I have three questions. It's a good paper, very nice presentation, and I have just three questions. One of them is commercial, and the other is technical. What is the approximate cost of this pan-analytical CNA bauxite analyzer and the Foxborough conductivity sensor? Approximate cost.
Well, there has been a split of the responsibilities with Ashok. I started working rather on the conductivity meters,
Okay.
and what I can tell you that I sent out a request for quotation for actually the Rosamount Emerson, about 2 weeks ago.
Okay.
And to be fair, their response is slower than I expected. But I hope that as far as its cost is concerned, there will be reply within a reasonable time frame. Sorry, but right now I cannot tell you.
Okay.
Or,
Okay. No issues. No issues. My other two questions are see the bare liquor, especially the blow of the digestion slurry, is scaling type. So how this affects the measurement? Because what we had found is very frequently the sensor scales up and the results are not reliable.
wow. Shankar, this is a really valid point of yours. This is why I pointed out that two sensors are envisaged for a
Okay.
single digester line,
Okay.
and the frequency of scalings, which obviously needs to be done, depends on the extent of scalings.
Okay.
So that for the time being, this would be what the precautions what has been considered.
Okay. Okay. My last question is with respect to the calibration, the conductivity versus sodium hydroxide or aluminum. We have to do the physically the calibration. So how frequently the calibration has to be done?
Well, Sankar, this is something what we should clarify with the supplier. Let me say my guess is or my hope is that not more frequently than maybe once a month, but this should be verified.
Okay, sure. That's it. Thanks.
Okay. Now it's Mr. Kaushal Gupta. Please
Yeah.
go ahead.
Hi. All this question is regarding this online analyzer. Okay, so you have shown two one. One is the pan analytical, another the NIR. Okay, so definitely pan it was showing a more penetrical. So it was given maybe penetrical analysis also. In case of NIR, it is going to the surface analysis. Okay, but it could be that in case of pan analytical, it is showing the alumina and the silica, means total alumina and total silica. In case of NIR, it is going to give the THA and K silica also. So can you elaborate on this particular point?
Yeah. Can I answer your query?
Yeah.
Please note you are determining gibbsite and kaolinite content by your NIR technology. Okay. Gibbsite and kaolinite, these mineral phases. But gibbsite is not actually available alumina. Gibbsite is, in case in bauxite, there is more reactive silica Gibbsite will not represent available alumina. Same way, kaolinite is not, all kaolinite is not reactive silica. There are fine quartz particles also reacts in this thing. So alumina refinery actually want available alumina and reactive silica. And that can be very easily determined from total alumina, total silica from one type of bauxite. If suppose you are using one type of, say, Eastern Ghats bauxite, you can do series of bondization tests simulating the plant parameters and also carry out a quantitative mineralogy and derive the formula. That's what done many places in the world, and we have established this kind of formula. So only mineralogy, only kaolinite and gibbsite is not enough. If the combination of both are there, yes, gibbsite, kaolinite, as well as the alumina silica, that is the best for alumina refinery. Then we can exactly determine the available alumina reactive silica. So combination of these two are quite good.
Okay, so at this stage, can we we can say kind of conclusion kind of thing, pan analytical is better than this NIR? That's what?
Oh, we are not telling something like that. We are telling that that's a total alumina, total silica is determined, which is more useful and which can lead to determine available alumina reactive silica. Only mineralogy will not be helpful. Only gibbsite content will not. Gibbsite is not available alumina. It's different.
Yes, correct. Okay. Okay, thank you. Okay.
Any more question? One, Mr. VK Vemuri.
Yeah, I wanted to correct one point which you mentioned, that NIR technology gives gibbsitic and kaolinitic. That is not correct. The calibration is done for available alumina based on the lab analysis of the bauxite. So actual available alumina and actual reactive silica is measured and given in the analyzer. It is not gibbsite as a component which is given.
Your basic is the mineralogy determination. It is derived from the mineralogical analysis. And anything derived from mineralogical analysis may not be correct. It is better to derive from total alumina and total silica.
When there are multiple types of bauxite mixed, like what they are doing, Mr. Kaushal Gupta is doing in his plant, imported as well as Indian bauxite is mixed. In that case, total alumina based calculation will be misleading. And in our calibration, I am trying to repeat again, in our calibration, we don't do the calibration for gibbsite. We do the calibration for available alumina. But available alumina is what is measured in the calibration samples.
But it is done through infrared spectrometer, and it is done indirectly. You are not directly measuring alumina and silica. You are measuring alumina silica via mineralogy, because your infrared technology you are applying.
Yeah, any NIR or any online analyzer will be based on calibration data. And here the calibration samples are measured for the constituent, and that is what is giving the analysis from the calibration model. So the actual measurement,
in all the process you can do calibration. You have 50 samples, you analyze by XRF, analyze by bondization, carry out quantitative mineralogical analysis, you can calibrate. And then actually this alumina silica results are more important, direct alumina silica analysis, not via mineralogy.
Anyway,
Mr. Kaushal Gupta, from you are Kaushal Gupta?
From Belgavi.
Huh?
From Hindalco, Belgavi.
Belgavi, okay.
Yeah.
Okay, any more questions, please?
Yes, sir. Good evening. I am from this side, from Hindalco. Sir, actually, I have 2-3 questions. One question is like two conductivity meter you were talking about. One were flow-through conductivity meter, and another was some tapered kind of conductivity meter was there. Which one would be more reliable? Because we do have a conductivity meter in the outlet of digester. But what we observe ki cascade control using that conductivity meter is around only 50 to 60%. So we are looking for something which can be more reliable than this conductivity meter. So,
George.
Beg your pardon. So let me say that my personal preference is rather the flow through conductivity meters. However, I cannot say that I have very deep practice in these two types of conductivity measurements. Therefore, in a real interest, we should discuss this question deeply with the suppliers, with the references, and so on. So, what I can say is that is right now rather my personal preference. Thank you.
Okay, sir. Next question is ki, like we were seeing ki, we are discussing ki we will have to calibrate this conductivity meter from time to time because of scaling issue, right? So can we have a formula how to derive this A by C ratio using that conductivity meter? So we have a conductivity meter, but we are not able to derive in Excel or somewhere else using that conductivity meter ki how that A by C is getting reached based on that conductivity meter.
Well, my preference is if necessary rather use a more frequent cleaning of the conductivity meters. So in order to provide that at least one of the two implemented conductivity meters give the let me say the real A to C ratio. So I think that anything else which tries to take into consideration the scalings, that I'm not saying it's impossible, but would make the operation quite difficult. Thank you.
Last question, sir. So we don't have a formula using which we can derive that AYC based on conductivity. Formula I'm talking about, sir.
Well, I am in possession of a landmark paper of George Fulford. This paper was presented in the light metals in 85. If you send me a line to my email address, I'm happy to pass that paper to you, and I think that can be a starting point for this exercise. Thank you.
And definitely, sir, we'll send you email from my side. And last question, sir, ki like we are talking about AYC and conductivity meter of slurry part. So is there any instrument or equipment through which we can predict TA and reactive silica on continuous basis of slurry? Like bauxite part we understood, but for slurry, is there any instrument through which we can predict or just estimate?
As per my best, so I'm not aware of such a device. What I can imagine, rather to test the bauxite with any type of bauxite analyzer, what you find reliable, and
Respected
because
gentlemen, sir, this is Sanjay
sorry.
here. Sanjay here. I would like
I'm
to.
sorry. I'm sorry.
Wait,
Let me
wait.
finish. Let me finish my reply to Mr. Kushwa.
Sure.
So because there is a time lag for the predestination, this allows you to make a good approximation, a good calculation for the composition of the solids, which actually leaves the predestination. That would be my reply. Thank you.
Mr. Shiv
Okay.
Kushwaha, provide your email address
Yes,
and you can directly interact with George, and IBAAS can help you in getting the replies.
Okay, thank you, sir.
Yeah.
Yeah, thank you, sir.
Okay, Sanjay Kumar, your question?
Good afternoon, sir. I was just addressing to Mr. Shiv Kuswa and György, sir, that during this sort of a slurry and all this mixing and all, does that smart couriers remotely they can control that, like analyzer, as we used to do in Autotech and all, when from the remote distance we used to control the slurry ratio and the mixture and sort of even the percentage of the mineralogy can also be controlled through those couriers.
Thank you very much. Your additions. This should obviously be taken into consideration.
Sensors, or there are special sensors are there. Can you please send details what you are referring, Sanjay?
No, this I'm talking about when I was associated with Autotech. We used to be for the Hindustan Zinc and some other of the places. There were automated, remotely controlled. You know, even they can control the slurry mix. Like when we used to do the vein pump and all, many slurries were going from the remote. You cannot control all the time. The ratios will change in the flow. So those ratios could be controlled based upon the final analysis report and all. I think many people who are into the slurry management and other, they must be knowing about the courier. These are very special equipment. Even Dr. György also and Nandi sir, you also must be knowing. Even Mr. Kushwa sir also must be knowing about it. Those couriers are very useful instruments. So I do not have ready Reconer with me, but maybe Metso, Autotech, and all those companies can give idea on it.
Okay. Thanks. Let us look into that. Okay, any more questions? Any more questions? And the presentation will be available on IBAAS website. And anybody wants to interact with George, please send your mail and we will mix it. Ivan Hiralal from Holland. Please, Ivan, ask your question. Ivan Hiralal. Hello, Ivan. Hello, Ivan. Ivan Hiralal is a renowned alumina technologist. He was working for a long time for companies like BHP Billiton, Rio Tinto. He's a precipitator expert. Ivan, can you hear me?
Yeah.
Tell me.
Can you hear me?
Yes, we can hear you.
Okay, I had problems unmuting. Okay, George, thank you very much for your very clear and very good presentation. I enjoyed very much. This is a very good subject for the alumina industry, and I noticed also based on the comments and the questions that you get that this is a very, very active subject. People have still problem with it, although the technology used in the industry is more than 20 years old. But I have one comment and one question. One is the success of this control system is very much dependent on the technology that you apply in your refinery, blend with a very good bauxite blending system with a very homogeneous bauxite chart to the digester will be more successful in controlling a more stable A to C ratio. And also the pre-desilication section is also very important. The larger surge capacity you have there, the more buffer and more homogeneous slurry you can feed to the digesters. So it's not always a problem with the sensor and the control method itself, but the bauxite homogeneity is also a key factor. That is one, let's say, comment. The second one is on the control, George, just your opinion on that one. my experience is that for the safety margin that you mentioned, that you're referring, that you're using as reference the solubility of alumina under the digestion conditions using Steve Rosenberg's equation. The equation is a very good equation, no doubt about that. But in an industrial environment, it is a combination between the behavior of your bauxite and the liquor composition. So more relevant is, I think, to use as a reference the breakpoint under the digestion conditions to define the safety margin. What's your opinion on that, George?
Well, first of all, I really I'm amazed of the knowledge and the achievements of Steve Rosenberg and Steve Haley. I have known both of them, and I respect them very much. In fact, when I made the development of my favorite path called improved low temperature digestion, and at that time I did not use these equations. I used another one from my mentor, Dr. Shikloshi. And in fact, my surprise, what I found that as you could see, that significantly larger A to C ratios were achieved than Rosenberg and Haley formula suggested. Let me say my personal opinion, obviously nothing else, that this formula, this equation, is perfect for temperatures up to, let me say, 100 and maybe 20 degrees centigrade, but at higher temperatures the accuracy of this formula is less. So I think one more thing, I did not it was not an objective for myself to make a thorough investigation on the equilibrium solubilities. What I wanted to show you, nothing else than there are some tests which raise questions about this formula in the range of a low temperature digestion. That's it, nothing else. Thank you.
Okay,
Yeah, the question was actually, George, to use the breakpoint as a reference. You mean normally when you design your digester, you do the laboratory test and determine the breakpoint, which is the A to C ratio at which you start losing extraction efficiency. So that would be the practical limit instead of, let's say, the equilibrium, regardless of the equation that you use for the equilibrium calculated equilibrium.
I think this is a valid point. You are right that when the extraction yield starts to reduce, that's okay. That's the break even point, and this should be approximated as much as the control system allows.
Thank you.
Thank you.
Is there any more question? Are there any question more? So thank you very much, everybody. The presentation will be available on IBAAS website, and you are welcome to interact with György Bánvölgyi, and please contact IBAAS office for further details.
Thank you, Dr. Nandi. It was a wonderful presentation. And thank you, György and Ivan and all the people. We really interacted and we knew the subject very well.
Thanks. Thank you very much. Okay, bye.
Bye,
Thank you
everyone.
thank you for your interest and
Thank you, everyone.
questions. Bye bye.
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 Okay, thank you. Bye.